All right, folks. How's the volume today? Folks in the back here, okay? Yeah, all right. All right, let's continue from where we were last time. We're talking about texture. And as a reminder, before we move on to minification, we just finished talking about magnification, which was the case where the texture image that we have is going to be projected onto the screen at a resolution that's higher than the image. And so we have to upsample or interpolate the image. And I said that's actually the easy case. Texture minification is actually a lot harder, which is not necessarily intuitive for most folks that start to think about texturing. It's not obvious that this case would be the harder one. But it is, and the reason is because many texels, that is, pixels in the texture image, can contribute to the final pixel footprint on the screen. And the shape of the pixel footprint can be complex, as you remember from our discussion on that at the beginning of last lecture. So the idea for solving this case from a filtering perspective and anti-aliasing perspective is that we're going to try to low-pass filter the texture file and downsample it. And we're going to need to do that for a successive set of lower resolutions. I'll show you what that means in detail. But basically a high-res image and then successive lower resolution versions of it. And then for each sample that we draw on the screen where we need to look in the texture image, we're going to choose the resolution that is approximately the same sampling rate as the screen sampling rate. That's the high-level idea, okay? And this should make sense because what we're trying to do is to apply anti-aliasing in its pure form, right? Anti-aliasing is filter out the high frequencies before sampling. And if we know the sampling rate on the screen, then this is the correct resolution to, close to the correct resolution to use. I showed this example last time, so if we have a low level 0 here, we'll be using a full resolution texture image. And I pointed out that if you look at the back and you have aliasing on the brickwork, and in the foreground it's okay, meaning that it's not aliased and about the right resolution. If you just look at the aliasing portion, as I increase the amount of downsampling, so here 4x4, it's less aliasing but still some, and then 16x16 downsampling will get us to about the right level of filtering in the background. Let me back up, and if you look in the bottom right corner, okay, where it's okay, the resolution at level 0. Here with 4x4 downsampling, you can already see some blurring, and if you keep looking at it with 16x16 downsampling, there's a lot of blurring. So spatially varying different portions of the image will require different amounts of resolution. And we can see what this looks like in by storing these successive levels of the texture in something that's called a mip-map. So mip-map is like one of the big ideas in texture filtering, and when it first came out, it really solved a lot of very tricky problems in texture mapping. The idea is to have these successive resolutions of the image. So in the top left, you have a 128 by 128 image, and we're just going to downsample it by 2x2 successively all the way down to at level 7 in the bottom right. It's a 1x1 pixel image. Okay, so all you're seeing here is the same size, but you can see the pixelation drawn on the screen in just nearest neighbor. In this case, a MIP map, very cool name too. MIP comes from the Latin multum in parvo, which basically means a multitude of things in a small space, which is pretty neat because one of the things that they were concerned about was how you were going to store a structure like this. And So Williamson's original proposed layout for this map looked like this in the top left. Okay, so if it's a color image, you can store the RGB as 3 sort of grayscale images, as you can see, here. So RGB components here, and then the next level of the MIP will be RGB here and RGB here. So actually, this diagram shows you can sort of see instantly what the overhead will be for this, right? It's a geometric series that converges, which is nice because the full amount storing the whole thing basically only takes an additional 1/3 storage space. Now, the next thing we need to figure out is when we're drawing through the screen, which level of this hierarchy do we want to use? So what's the mip-map level, which I'm using the variable d here for, okay? And to do this, you might remember yesterday I said you can sort of use basically, like a Jacobian of this transform that takes you from the screen space into texture space. You can use the Jacobian to figure out from the partial derivatives of this change what the projected footprint of the pixel is. Okay, so what we're doing here is if I want to take this texture sample, I can look to the north and to the east and say, well, what those pixels are in the screen space will help me to estimate how big this footprint is on the texture space. You can see for this sample here, it has a footprint that looks like that. And for this red sample here, it has a footprint that looks like this, so it's larger. And in particular, all you need to do is look at the projected coordinates for those in order to get an estimate for this vector here and this vector here. This is du dx, dv dx here. And okay, so we're going to define this level d here by using this length L. What's L? If L is 1, then one step in the screen space is going to take one step in the texture space, so we want to use the base level resolution, the full resolution image. If in this case, if you eyeball this, it's about, a little bit over 2 pixels, maybe 2.2 or something, we want to use one level down. If it was 4 pixels wide, then we want to use 2 levels down, and so on and so forth. So this length L, if we take the second log of it, log base 2 of it, that will give us how many levels down in the middle we want to go. And L here, this length, you might be like, well, maybe this one's short, maybe that one's long. So simple heuristic here is to just take the maximum of it. I'll come back to that a little bit later in the implications of it. You can just take the maximum of these 2 vector lengths here. Okay? And so the estimated, pixel size that we're talking about is kind of L large here. And this is similar to the size of the projected collecting area for the mip-map level that we're going to be using. Here's a visualization of the mip-map level for that scene I showed last time. So here is D rounded to the nearest integer level. Red is, one MIP level, and yellow, green is one of the different successive MIP levels. And one thing you can see is that, okay, if you take it rounded to the nearest integer level, then you're going to have discontinuities where the pixels that we're sampling in the red region here are going to use one MIP level, and the yellow will be the next MIP level, which is actually also a discontinuity of its own, right? So there's sort of a high frequency change there, if you will. So a simple idea is to try to ameliorate that and introduce an even higher level of qualities to do trilinear filtering. So linear filtering in 3 dimensions this time. And this is, say, mip-map level D, and this is mip-map level D plus 1. So this just shows, okay, we'll use these 4 pixels of this resolution, and we use these 4 pixels of the lower resolution. We can take a bilinear interpolation of each of these. We talked about that last time. And then you can basically linearly interpolate between the resulting color that you got from each of them. You can blend them based on the continuous D value. So if it's 1.0, use this one. If it's 2.0, use that. If it's 1.5, use the average of the two. Okay? And if you do that, this is a visualization of continuous D filtering. You can see how you blend between these. So particularly if you're animating, this will cause all the changes in the scene pixels, especially if it's moving in time, to be smooth over time. You won't have these discontinuities between where you use different levels. The cost of this, remember, our goal was to enable anti-alias filtering of textures, not with a multi-sampling or a super sampling approach, but rather with close to ideally 1. Or at most a very small constant number of samples. So in the case bilinear resampling is going to use 4 texel reads. That's 3 lerps. And this trilinear resampling is going to take 8 texel reads. So we read 8 values and then do 7 linear interpolations. Your assignment, you're going to do, basically nearest or bilinear, and then whether you always use the full resolution, the nearest view, or do the single resolution. So you implement a few of these and kind of see what it looks like for yourself. So how does this look? Point sampling here. There's some limitations to trying to do maps, okay? It's a really great solution. It gets us a lot closer to avoiding aliasing problems, but this is the high quality example. Okay, super sampling with 512 samples. This is mid-map trilinear sampling. Back up again. So this is super sampling, anti-aliasing. And if you look from the bottom to the top, you can sort of see where things seem to break down. Now you don't have any aliasing on the top, but we've lost a lot of detail. So it's over blurred in this region. Okay. Why would it be over blurred in that region compared to super sampling? Why do you think it's blurred more than super sampling? Anyone have a thought on that? Say again? Yeah, everything at this distance high up here is getting projected to like a very low, high level on the MIP or very low resolution version of the image. It's all getting blurred out. Okay, that's exactly what's going on. Why is it being estimated like this? Where's my cursor? Let me take it back to a slide that we had yesterday. So this was the image, and this is the picture of the footprints. The footprint for this line here is a long, diagonal skinny strip here. What are the derivatives of the two components of this, L vector that we're going to be using are? It's going to run along the axis here and along that axis there. So it's one very short component, one very long component. And in the formula for the MIP, we're using the long component. We're taking the max value. So we're going to take this long diagonal and assume that we're going to integrate over a set of pixels that roughly look like that big. Okay? So instead of taking a small integration of this set of pixels, we're going to take an integration of a set of pixels that look like a big box. That's the reason why it's going to look very blurred. That's why it looks very blurred in this image here, okay, compared to the right answer. Because in the background, we're integrating too many pixels. And this is sort of a tricky problem to get around with this particular approach. A different one you can use is something called elliptical weighted average filtering. Intuition should, start to lead you down the path of thinking, how could you get around this problem? Basically, you need to be a little bit more careful about the filtering, particularly for these diagonal approaches. And there's two sort of approaches for what's called anisotropic filtering, where anisotropic means not the same in horizontally and vertically. One is called RIP maps. The other is called EWA, elliptical weighted average filtering. So RIP maps, and similar to something called sum-area tables, you can get a sense of what's going on with this picture on the right. Okay, so this is a RIP map. What we're doing is we're averaging horizontally, sequentially, and vertically, sequentially. So the MIP map lies along, it's a superset of MIP map. The MIP map's just along the diagonal here, right? You get images that are flowing. So you could use this, and that will help, right? Give us some filtering in things that are axis aligned, anisotropic. But for things that are diagonal, it's still going to be kind of problematic. So elliptical weighted average filtering tries to get these diagonals by taking a few samples that could shape better to the diagonal, the size of the footprint diagonally, integrate those. You can use a MIP map here as well. You have one big, sample in the middle and then a few successive smaller ones. Not a common project in the past, but I was thinking about it as a preparing lecture. I was like, doing a study of these different filtering techniques and the trade-offs. It's actually a really intellectually rich project. Maybe a project idea for a team. Okay. Let me come back to advanced texturing if we have a bit of time. It's more informational. Let's move on to the main topic for today, which is the rasterization pipeline. Okay. Let's just put some of the pieces that we've been talking about together and then fill in some of the remaining gaps in a first pass of this graphics pipeline. Okay, so we've studied transforms, how to pose objects in the world and the camera in the world, compute the positions of objects relative to the camera, project them with perspective onto the screen. And we talked about how to sample it in rasterization. how to put color coordinates or texture coordinates over it and interpolate those across triangles and apply texture maps with filtering. Okay? And so, what does this get? What does that get to us? Get us to? So here's a rendering, a little animation. It doesn't look quite right. Okay, so we're missing a couple of things. If you look at it a little bit, the longer you look at it, you're like, well, I think it's supposed to be like some cubes in space. It sort of, okay, it sort of seems some cubes in space, but then it's sort of weird, like some far things. I don't know, it just looks weird, right? So what's missing? Okay, so here's a different version of it with just two additional things that we want to talk about today, okay? And this one I think would just be a lot more recognizable, okay, as a realistic looking 3D rendering. And I'll just go back to this, the previous one. Okay, so here it is again. So one thing you notice is that each of the cubes is a flat color. Okay, that's obvious. So we need to do shading, which is going to give us some lighting information. The other thing is that, okay, if you look at the top, see that yellow cube? Let's just keep going. Look at the top row. Okay, look, that blue cube appears in front of the yellow cube. It's so weird. And now, because the blue cube should be in front, right? Oh, but the yellow cube is in front of the other guy. It's sort of a bit weird, okay? Okay, so that's one thing. We're going to talk about that. That's basically depth ordering. Hidden surface removal is the name for it. And then the other thing is the shading. So there are two things we'll talk about today. What else are we missing? Okay, if you look at this, okay, this is a hyper-realistic, photorealistic kind of rendering. What else are we missing? There's a lot of geometric detail in here, from the cups to, the cutlery to the shape of the foam on the coffee and things like that. Here's another picture. It's also a rendering. In this case, right, you can see the flapping of the hummingbird here. The wings have motion blur, right? If you look at the background, that flower is kind of out of focus. That's depth of field effect. These are lens effects and camera effects. Okay? So, geometry, lighting materials, and camera models are additional things that we're going to be talking about. And here's sort of a course roadmap from where we are, where we're going. Okay? So we've talked about rasterization, transforms, texture mapping, and today we're going to talk about visibility, shading, and how they fit into the overall real-time, or graphics accelerated graphics pipeline. Then we're going to talk about geometric modeling, which will have a series of lectures pretty much similar to the number we've had already, lighting materials, and then camera and imaging. Okay? So visibility today. Visibility. Visibility just means what can we see in the image, and in particular, what can we not see because it's blocked by things that are closer. Okay? That's what visibility is going to be about today. And in that animation I showed before, the first one, visibility was wrong. Okay, and we're going to see how to fix it, or how it was fixed in the second one. So here's an algorithm that can solve this visibility problem correctly, which I think is pretty intuitive. Okay, it's inspired by how painters will paint, and that is they paint from front to back. Right, they paint from back to front rather. Okay, if you paint from back to front, then the stuff that you paint on top is going to just paint over the stuff that's behind it, and it will hide it. Okay, so you sort of build up layers, right? And in particular, if we do it digitally, we're going to overwrite what's in the frame buffer. So if you draw from back to front and just keep writing over the values in the frame buffer, that'll be Painter's algorithm. So here's a little picture. So you draw the mountains in the background, and you draw the meadow in the foreground, you draw the trees on top. Okay? Then everything sort of looks right. Now, of course, if we did it in the reverse order, we draw the trees, then we draw the meadow, which would block all the trees, and then we draw the mountain, which would block part of the meadow. So you'd see like a mountain and part of a meadow underneath and no trees, which would be wrong. That's sort of what was happening in that first animation before. With things that interlock a little bit more, you need to think about it. Okay, so here's a cube, right? So if we draw the back face of the cube, then a side of the cube, then the bottom, and we draw it in the right order, at each stage will be a coherent 3D object, and you draw the front, and it's going to hide the interior of the object too. That will also be Painter's algorithm. Now, the thing with Painter's algorithm is that it's going to require sorting, right? We have to sort all the primitives, the triangles of the scene, from back to front, which is complexity n log n. So that's one sort of not great thing about it, because we might have a lot of triangles. Some scenes could have tens of thousands, if not millions of triangles, depending on real time or offline for movies. And another problem is that you can have unresolvable depth orders, even just from a pure, like completeness and correctness. if you have triangles that sort of interlock in depth like this painter's algorithm is not going to resolve that correctly. So then you might say, well, what we need to do is from the perspective of the camera, we could clip each of these, triangles into smaller triangles and then, find something where you can have a distinct ordering. It gets complicated, and there were many, many hidden surface removal algorithms that were created to try to solve this problem. The one that won out is basically the sampling-based approach. Okay, it's very brute force, and yet it's very effective, and it's basically the one that won out in most of the graphics. It's called Z-buffer. And the idea is very, very simple. It's that we're going to store another memory buffer with the colors in the frame buffer, and this additional memory buffer is just going to store the depth of the scene. So if we just store the minimum depth in the scene that we've currently drawn, that will give us the information to implement a painter's algorithm pixel by pixel. And that's called the depth buffer or the Z buffer. Okay? So here's a rendering. Here's a visualization of the depth buffer on the right-hand side, which you usually don't see because it's behind the scenes. Okay, so let's just spell it out. It's pretty intuitive. What do? You initialize the depth buffer to infinity. Then you just start drawing. You don't have to sort. You can draw in any order that you want. For each triangle, for each sample XYZ that's rasterized in the triangle, what we do is we take the Z value of that sample and we compare it to the current value in the Z buffer at that location XY. If we're the closest sample so far, then we overwrite that Z buffer value to the current, newest closest, and we draw the color into the frame buffer. It's simple. And then if we're not the closest value, then we just do nothing. Okay? So the color just never hits the screen because it's further away than something we've already drawn. So that's Z buffer. Okay? And here's a visualization. So if we draw a red triangle, as you can see, say all at depth 5, then when the frame buffer here, we'll have the triangle in it, width stored with its depth 5. And then we draw another triangle, and if you look closely at this, it's basically a tilted triangle in depth. 3 is closer, right, than 8. So we draw it, it's gonna partially clip off the other triangle. And so all the values here that are closer than things that are in the frame buffer will get drawn. And you'll end up with this interpenetrating triangle square. The complexity of this is just linear. It's O(n), right? Which is sort of interesting because, how can you sort n triangles in linear time? Can't do it. Turns out we're not sorting the triangles in this case. We're just resolving it at the samples that we're generating from the screen. Okay? So sort of recognizing how we can repose this in a sampling framework. Yeah, question?
So is this sort of a so that you're not just using the value of the data, but you're using the actual values? And then you got
Yeah, that's interesting. Yeah. I think you can think about it. I mean, there's an analogy there. The thing is that we're leveraging the complexity of we're drawing so many samples onto the screen, right, in order to resolve the issue that way. Rather than saying, because we never really have to order all the triangles, it turns out, in order to resolve it on a pixel basis or for a sample basis. Okay, Z buffers implement all hardware. Yeah, another question? If we have a camera, and through animation we're changing the position of the camera, say for a world that's mostly static, is it reordering, ask the second part of the question again, is it reordering the triangles? Yeah. Is it reordering all the geometry as we change the animation, things like that? That's a great question. Let's just think about this, okay? So if you write your program, what's one way to write it? Here's a list of all the objects in the scene. Here's a list of the triangles that compose those objects. And remember the graphics pipeline? We emit all of those vertices down the graphics pipeline, and they describe triangles. It goes through rasterization and so on and so forth. The way that the camera works is that we have transforms that are sitting, I'll come back to this when I do the final wrap up of the pipeline. At the vertex portion of this pipeline, when we send the vertices in, they're going to be transformed by a matrix. That's where we're going to see model view, modeling matrices, the camera to world transform, the perspective transform. It'll give us one 4x4 matrix that we multiply each of the vertexes by. So all that's happening, right, is that the vertexes go through, each one gets multiplied by a 4x4 matrix to determine its final location on the screen. And then a triangle is determined by 3 vertices, and it gets rasterized. So are we reordering the geometry when we change the world transform or the camera position? No. Okay? So the geometry is just getting emitted in exactly the same order. Just this 4x4 matrix is changing, which is changing each of its projections onto the screen. It's totally changing which samples are being created during rasterization for each triangle. But the Z-buffer algorithm doesn't know any of that. Ordering is resolved just by that comparison that we had in that sort of thing. Good question. Hopefully that will be another layer on visualizing what's going on. Anyway, it's so important. It's implemented in hardware, used by OpenGL, lots of other things. Effects, all those kinds of things. Okay? Alright. Before we move on to shading, it's attendance time, so. Okay, so visibility and visibility resolving algorithms is how we solve that, which cube's in front of which cube in the animation at the beginning. The second thing was that the cubes in the first rendering were just one flat color, right? Flat blue, flat green, and that makes it really hard to interpret their 3-dimensional shape. The second part is that I want to talk about today is a simple shading. Okay, a simple shading model which goes by the name Blin-Fong. This is a reflection model that allows us to determine which colors a surface should be based on its geometry and how it's pointing towards the eye and the lighting, or the relative orientation towards the eye and the lighting. Okay? So what we're going to cover today is a so-called local shading model. This is very simple relative to the more physically based techniques we'll talk about later in the course. It's per pixel implemented, and it's very fast. It's very good for graphics that's accelerated for GPUs, and it's where it arose for real-time graphics originally. It's based on perceptual observations, not physics. What we'll cover later in the course, not today, is physics-based lighting and material representations and a so-called global light transport as opposed to this local one. The global light transport simulation is going to require us to evaluate things that not just at a per pixel and then done. We're going to have to worry about the transport of light from one location of the scene to another, back and forth through bounces of light. Really, really cool stuff. I think some of the jewels of computer graphics. But today, it's things that are more amenable to real time. Here's some perceptual observations about common classes of materials, okay? Here's a kind of plasticky material. Some observations. In the top right, you can see something we call a specular highlight. This is sort of like the reflection of the light source, right? So you can sort of tell there's maybe like a window off to the right-hand side. In the middle, you can see something we call diffuse reflection. Diffuse means basically that the light that's coming there is scattered in all directions equally. And that gives it sort of the intrinsic color of the object, okay? So it's a blue, cyan cup, yellow cup, and orange cup. That comes largely from the diffuse reflection. And then the ambient lighting term is here. It's like this part's like doesn't even see the light source at all, right? The window's on the other side of the object. But it's not black. And one of the reasons for that is that the light is bouncing around the room and hitting the cup from the other side as well. That's sort of, we call that an ambient lighting term. So I'm going to tell you about each of these, okay? Yeah, question. Yeah, good question. These are sort of names that were given phenomenologically. Basically, the ambient term is going to be a constant, okay? It's going to be approximated here as a constant in the simple model, and then the diffuse term is going to depend on the orientation to the light. So hold that question and it'll become, you see the mathematics for it. Okay, so local shading, what we need in order to do this calculation are a few pieces of geometry. And those things that we're going to look at are, okay, number one, I want to know which direction the viewer is. So then I'm going to color this calculate the shading color for this point on the surface, I want to know which direction is the eye, the viewer, which direction is the light source. You might have multiple light sources, so you would just do this once for each light source, okay? And then what is the surface normal? So all these would be sort of significant. And then I also have some surface parameters, like how shiny is it? What is the color? Was it red, green, or blue? Okay, those types of things. Okay, so let's see how they go together. So the diffuse reflection model is based on a model where the light that comes into the surface is going to be scattered uniformly in all directions. It's also sometimes called Lambertian reflection. It's the same in all directions. And the brightness of how much is reflected is governed by something called Lambert's cosine law, which is fundamental. Okay, it's a fundamental geometric feature of illumination and how illumination calculations work. The thing that we want to know is, let's say that you're outside in the sun, okay, and I put a little cube here. How much energy is going to fall on a tiny little patch of the surface? And it turns out it's going to be different if it's pointing this directly at the sun or if it's tilted at the sun. It should be sort of a little intuitive. Okay? If you point directly at the sun, it's going to be hottest. And if you turn it more and more as you get towards glancing, at least that point will gather less and less energy. If it tilts away from the sun, it'll be in shadow, get nothing. And you can see why that is. If I tilt it 60 degrees to the light source direction, only half the rays are going to be striking. That's a simple sort of trait. Trigonometric kind of effect, okay? But fundamental to how illumination and transfer power works in a volumetric sense. So the key thing that we want to figure out here is what is the amount of power that's falling on here. And to do that, you want to know it's going to be based on the cosine of the angle between the lighting direction and the normal direction, surface normal direction. And particularly, if you just take a dot product of the L and the N vectors, normalized vectors. Okay? The second part is that light will fall off as you get further away from the light source, if it's a point light source. So let's say you have a point light source here. The intensity here, okay, if it's I at the unit distance away, then by the time you get to R units away, it's going to fall off as R squared. And that's easy to see because the energy is conserved as it propagates out, and it's going to be on a surface area that's the 4 pi R squared surface area of a sphere, right? So it falls off as R squared. So the Lambertian diffuse shading model, a diffuse shading component rather, is we'll say, okay, L sub D here will be our term for the diffusely reflected light. What we have here is, okay, here's the cosine term, n dot L. We're going to take a maximum of that against 0 because, n dot L can go negative, right? If they're pointing in opposite directions, bigger than 90 degrees, you get a negative value. But you're not going to reflect negative light. It's going to clamp out at 0. Here's the I of R squared fall-off term. And then we just have a multiplier here of diffuse coefficient. This is basically like, what is the intrinsic sort of brightness of the material? Okay, and what color is it? Red. So you can think of this KV as a color. Okay. What does it look like? So as you change case of D, okay, you just if it's a grayscale, you just get darker or brighter, depending on what case of D is. And it produces a matte appearance, a diffuse appearance. The walls here are not painted, but they're pretty diffuse. If you want to look at almost any wall that's not deliberately trying to be shiny, usually you want walls to be very diffuse, okay? So they don't show imperfections as much. Shinier things will show imperfections more clearly. So light that strikes, they'll just get scattered equally in all directions. That means that if you look at the wall from different directions, one point on the wall, it will be basically the same brightness. That's what you see here too. That's not true of the specular term. The intensity depends on the viewing direction. When I just say for diffuse, you can move around from the wall, look at the same point. It doesn't matter what the view direction is. It's going to be the same. In specularity, or shininess, that's not true at all. If you start paying attention, if you haven't thought about this before, you start paying attention to it. Look at something shiny, and as you change your viewpoint of it, like look at one point on it, like I look at my ring here, I can look at the surface of my monitor, and if I reflect off on that point, there's something in the background, it will change its color of that surface point very dramatically. So the viewpoint really matters here. And in particular, this specular shading model, which was developed by Bui-Tong Fong and Jim Blin, it's sort of a hack that produces phenomenologically this kind of effect. What it is that there's an observation that usually the reflection portion is brightest when you're near the mirror direction. So what does that mean? So if you have a glass and mirror surface and you have a light source, the mirror direction, right, is the angle that gets reflected off the surface like a mirror would, symmetrically around the surface normal. If you put your eye right at the mirror direction, then you're going to see the light source, so it'll be very bright, the surface point. Okay? And the closer you are to that mirror direction, the brighter it should be. That's sort of what the intuition was for these folks. They try to make, early computer graphics algorithms that look sort of like the real world, okay? And they don't know how to do shading yet. So this was a phenomenological attempt at it. So, what's actually done is, the intuition is it's right near the mirror direction. Close to the mirror direction is very similar or equivalent to the half vector being near the normal. So what that means is that if my eye is close to the mirror direction, that's going to be the same geometrically as if the half vector is near the normal. So what's this half vector? The half vector is just the bisector between the view director and the view direction rather and the light direction. So there's the light, there's the view, and if we take the bisector between them, which is easy to calculate because we just add them together, okay, we add the two vectors that will give us a vector that's in the direction of the bisector. You have to normalize it too. Then they'll be close. When they're close to the mirror direction, this half vector is going to be very close to the surface normal. I think we can see geometrically. So the angle between the normal and the half vector is something that we can use and study that angle on. Okay. And in particular, what we can do is here's the model. As you can notice, it's very similar to the diffuse shading model, except that this term here is cosine of alpha. And it's raised to a power p. This alpha term here, right there, right, it's going to be the dot product between n and h. Half vector and the surface normal. And then raised to some power p. Now what's the effect of this? Okay, so basically what we've done is the cosine between the half angle and the normal vector, raised it to some power. If it's raised to the to power 1, then you just get cosine fall off. 2 is cosine squared, cosine of the 8, cosine of the 4. So all we're doing is we're taking a lobe, cosine lobe, and we're trying to make it sharper and sharper, closer and closer to a point. If we're at the mirror direction, if it's a perfect mirror, the only light reflected should be in the mirror direction. If it's very shiny, it will sort of scatter a little bit about the mirror direction, and if it's less shiny, it will scatter more at angles that are a little bit far away from the mirror direction. So if we wanted to be a perfect mirror, we would raise the exponent to a very high number. Okay? Here's what it looks like. So here, down here is basically the case of S. This is just like how, what's the multiplier on the shiny component on the specular highlight. And then here is a raising P. Okay? So if P is a small number, then you end up with a broad specular highlight. That's this shiny spot here. And if you raise it, you can end up with shiny and shiny points. Yeah, so it's sort of like rough plastic versus shiny plastic, or rough metal versus shiny metal. The third component is the ambient term. The question about this before? So it's basically shading that doesn't depend on anything, okay? And the reason that this was introduced is that if you just use this Blin-Fong shiny term and the diffuse term, your renderings look very dark. Because there's lots of portions of your scene that are facing away from the light sources, and they're just pitch black. And that's very unnatural in the world. That just never happens, because in the real world, the light sources will bounce off materials and scatter around the scene, and those stray photons will never allow you to have almost pitch black shadows. Question? Is there any logic to how you pick the term P? Very good question. How do you pick this P term? And the answer is, it's a phenomenological model, which is to say, you just sort of like want it to look a particular way. So you tune the P until it looks kind of how shiny you want it. That's basically how you did it, and how you would do it too. Now, you could ask, your questions, I think, are a very good one, because you'd say, well, let's say I want to replicate a real material. Like, how do I pick it for that? Okay. That's a different question, which is sort of like, how do we take the structure of a real world material and represent it and its reflection? It turns out you need quite a bit more structure than that. We'll come back to that later in the course. One of your TAs, Lin Chi-Yan, actually is a real expert on this, and so I think we'll arrange for it that he can give you some lectures on that. Okay, ambient term, very simple. Total hack. Okay, the hack is this is a constant term you just added in. Okay, so You pick some constant term K sub A and you just add it in. It's helpful for making your shadows not look so dark, which you can see here. So here's the ambient term for some kind of, bulby object here. Here's the diffuse term. It looks just like a matte paint. And then the specular term, which is where all the highlights are. And the sum of those three terms gives you this final function. Okay. The next thing I want to talk about is when you actually put this shading model onto triangle meshes, what's the shading frequency? That is, what is the frequency with which we're going to calculate this shading? And the reason this is important is that even for a simple, relatively simple mathematical model like this, calculating shading turns out to be one of the most expensive functions, much more expensive than rasterization and visibility checks. And it turns out that shading simple of this kind will get much more complicated as we move to realistic materials. And so the frequency of shading in graphics has traditionally been something where you want to save compute time, accelerate, by doing this as infrequently as you can. So what are some frequencies over which we can do this based on the current architecture we have for this graphics pipeline? Well, one thing is we can just shade each triangle. This we call flat shading. It's also called Gouraud shading, okay? So here you can see what we've done is that for each triangle we have a surface normal, and we've done this shading calculation, which you can imagine as it goes down the graphics pipeline, you can do one per triangle, and then that's the color you just draw for all pixels on the triangle, right? Doesn't produce very smooth looking surfaces. You can see the facets and the change between these triangles very, very distinctly. The first one's called flat shading. This one's called Gouraud shading. We can shade each vertex in turn, and then interpolate them across the triangle. And you can think a little subtly about what's happening here. So instead of each triangle having a surface normal, what we're saying here is that each vertex that we send on the pipeline, we're going to assume it sits on some surface, and we're going to assign it a surface vertex, which may not be correlated with its triangle's normal. In particular, since this is a sphere, we can take each vertex, and instead of its triangle and setting it to that surface normal, we can say, no, here's the true spherical normal direction, and assign it there instead. And then we could use the interpolation that we talked about, the barycentric interpolation, and interpolate that across each triangle. And you're going to smooth the result. In fact, if you look at this, this is a shiny ball eventually, okay? Just a very low resolution one, so we can see the problems. The highlight doesn't look very good because it's very high frequency. Right? A fast change in a small area. The diffuse shading is slowly varying, and so it actually looks fine at pretty low resolution meshes. The last thing we can do, which is sort of the highest frequency, is we can shade each pixel, each sample on the screen. And in this case, how we would implement this is that we set the surface normals at each vertex on the mesh, and then we're going to interpolate the surface normals across the samples that are generated on the triangle in rasterization, so that surface normal will be varying over the triangle. And then this n.l and n.h model that we talked about, we'll evaluate those with this changing vertex per pixel. So once per triangle, once per vertex, once per pixel. And you can see the sort of reduction aliasing artifacts that we have there. So if you have a mostly diffuse model, then pretty low frequency shading can often work pretty well. There's an example of the shading frequency and how they sort of vary. So if you increase the number of vertices, then you just have a lot of triangles or a lot of facets. So even the flat shading model with enough tessellation of your mesh will look fine. But if you want to use fewer triangles and then put the work into the shading, then these different shading models here can really help. In particular, this one here, this is sort of on the boundary of the highlight being okay. If the highlight wasn't there at all, it'd be difficult to distinguish this ball from this one. And then here, they're all essentially at the same sampling frequency because the triangles are the same size as screen pixels. How do we define the per vertex normals I talked about? I'll give you a simple example of a sphere. So each of the triangles on the boundary of the sphere here, the facet is pointing in a particular direction, but the vertex that's on the sphere is pointing out in the sphere direction, that's sort of best, okay? If you know what the underlying geometry is, that'd be great. But what if you scanned it with a laser scanner, or a 3D camera or something? So you just end up with a bunch of points in space, which you can tessellate into triangles. So how do you decide what the vertex should be of each triangle? So one thing that you can do, it's a very common scheme, is you can just take each triangle which has a well-defined surface normal, this is a portion of a plane, and then you can average the faces around a vertex. You can average the normal vectors to decide on a vertex for each, a normal vector for each vertex. If you have a vertex at each normal at each vertex rather, one here and one here, how do we decide intermediate normal vectors? Well, ideas we can do some barocentric interpolation on each of the components of this vector and just interpolate them. You might notice if this is a unit vector and this is a unit vector, this one is not going to be normalized. So one question is, how do you adjust the length of these? If the difference between the vectors is not too great, then linear interpolation, barocentric interpolation will keep them roughly unit length. But if they're very far apart, you might end up with a big discrepancy. And if you imagine using this n vector in an n.h or an n.l situation without normalization, it's going to change the value of that outcome quite significantly. But you might want to try and cheat because normalizing this will require computing a square root, right? And you're going to do that every pixel sample that you generate. That could be very expensive. These are the kinds of trade-offs and considerations that will happen in a real-time rendering system where you try to run at a very high rate. Okay. That's what I have to say about this local shading model. Let's take a look again, zoom back out and look at the rasterization pipeline. Okay, so here we go. Here's the application. We got vertexes in space. We put them into the pipeline, which has vertex processing, goes through the triangle processing that generates pixels through rasterization. Remember those pixels I mentioned in GPUs when we do super sampling, they're called fragments, is the name we give them. We got fragment processing, and then it goes to the frame buffer. And in particular, the vertex stream here, this is the diagram of what I'm showing here. So vertexes, position in screen space, you get triangles, you get fragments, we shade the fragments, and then we go to the frame buffer. The modeling and view transform that we talked about happens at the vertex processing location. We generate a 4x4 matrix through our modeling and perspective modeling process. It affects all the vertices. This rasterization process happens here from triangles being turned into fragments. The evaluation of these shading functions can happen either at the vertex stage. That'll be things like that per vertex shading, the Gouault shading, or it can happen at a per pixel level, in which case it would happen at this location in the stream, for things like Phong shading. Texture mapping, something happens at the vertex stage in order to calculate the texture coordinates. And then at the fragment stage, in order to perform these memory lookups and these filtering operations that we looked at. And then the Z buffer tests to resolve what's closest. Those will happen basically at the frame buffer. Now, one nice thing about this pipeline, and this wasn't true historically as it emerged, but over time, this pipeline got very generalized from a machine perspective and then from a programmability perspective. So, of course, these days, one great thing is that the vertex and fragment pipelines are highly programmable. This is an example of a vertex of a streaming shader program. This is in the GLSL streaming language. So this function that you can define basically will apply to process each vertex as it goes through the machine at a very, very high rate in parallel. This shader function will execute once per fragment. Okay, it's a per fragment kind of program. And what it's doing is it's going to output the color of the surface that we want to put into the frame buffer. And this particular shader here is going to perform a texture lookup, okay, to obtain a surface material color and then perform a diffuse lighting calculation. So just very briefly, the syntax here is that, there's these global parameters. This is like the texture object that's applied, to the surface. Here's a lighting direction. This is like global to the scene. Then there are these values that are basically interpolated by the rasterizer. This is the per fragment value. This is keyword varying. This is the UV value for texture lookup, and then the surface normal vector for Linfang shading. And then inside the shader itself, there's a texture lookup here. There's a dot product that's happening here. And then this GL frag color is basically a keyword for the fragment, for the frame buffer value that you're going to overwrite or you're going to write into. Okay. So you can express all of these things. The reason that a lot of these things were generalized is because the richness of shading calculations for lighting and for other, even for not lighting calculations, but even for doing physical simulations, like grass movement and so on and so forth, were generalized out of these programmable vertex and shader programs. So now there's a GPU, right? You've heard this term, general purpose GPUs. You can express very general computations. And some of the goals are to, do hundreds of thousands to millions of triangles in a scene, do very complex vertex and fragment shader programs, and generate pretty high resolutions. So 2 to 4 megapixels, maybe even 8 for 4K these days, and 30 to 60 frames, maybe even 90 frames for VR. And of course, that's possible because things have been really optimized in GPUs. This is a Titan X here. This is the layout for a GTX 980. These machines got very complicated in order to keep this data parallel architecture hot. One way to think about this is, jot some of the numbers down here. This thing has 2,048 arithmetic units on chip. And each can perform a floating point multiply add operation per clock. And this thing was clocked at 1.1 gigahertz. So this thing could do 0.6 teraflops of compute. And the reason is that the way we structured this graphics pipeline and the nature of the operations that are allowed in here enables the GPU architects to go full parallel on data parallelism through this architecture. And it's taken a lot of care to be able to generalize the kind of programs that you can run in the inner loop while maintaining the efficiency of this parallelism. All right. Let me just make a comment. I was afraid I wouldn't have quite enough time, so I skipped over it. But it's going to be in the slides for you. We just jump back to the texturing lecture. So at the end, for those who are interested, you can go and take a look. There's a bunch of different texturing methods that use what we talked about for using these values. So you can do things like represent environment maps for reflection. These could be texture maps that you put in and try to use them to have the color of the lighting in the scene be very complex. You can use cube maps as something that you can use to represent these spherical functions. You can use textures to describe displacements. So this surface here is actually a smooth surface that has a texture that's describing locally small deformations of the surface. They can add a lot of surface detail. Or you can just describe it, use the texture to describe how the surface normal is being perturbed very slightly. So people have been very creative in their use of data passed through textures that are filtered to the GPU to enable a lot of geometric and lighting material detail. And really only limited by the creativity of what you can write and express in these shading calculations. Thanks a lot, folks.